The goal of this lab was to use Faraday's law and examine how a magnet falling through a non-ferrous tube induces a current in the tube, which in turn produces a magnetic field and exerts a force on the magnet as it falls. These are the fundamental physics principles used. Faraday's law predicts how an external magnetic field, in this case from the magnet, affects the conductive tube and induces an electromagnetic force in the tube. Lenz's law states that the change in the magnetic flux is equal and opposite the EMF of the loop. We also use the Biot-Savart law to find the magnetic field and force from the dipole magnet. Newton's second law states that the force on an object is equivalent to its mass times acceleration. And finally, Newton's third law states that for every action, there is an equal and opposite reaction. Now for a brief overview, I first performed an experiment with a dipole magnet in an aluminum foil tube and measured the time it took for the magnet to fall through the tube. Then I used GlowScript to make a computational model of the magnet falling through the tube and compute the time it would take for the magnet to fall in an ideal situation. And lastly, I compared the times from the experiment and the computational model. So for the experiment, I first found the north end of the magnet using a magnetometer. I dropped the magnet through the aluminum tube with the north pole on top, which means the dipole moment was pointing up. I repeated this 5 times and found the average time it took for the magnet to fall through the tube to be 0.533 seconds. Overall, I observed that the magnet falls much slower through the tube than it does falling in free space. So why can't we use a ferrous tube? Non-ferrous metals are not magnetic, while ferrous metals are, so if a ferrous tube was used, the magnet would have an attraction with the size of the tube that would alter the results. Now for the computational model, I first established my measured values, which are listed here. I used the dipole moment found in Lab 3, which was 6.3404. I then wrote a function to find the magnetic field at an observation location on a ring of the simulated tube. I used the Biot-Savart law for a dipole magnet to write this function. Then I wrote a function to calculate the rate of change in the magnetic flux of a ring of the tube. This function is derived from the equation for the magnetic flux, which is shown. Next, I wrote a line that would calculate the current of a ring. This function uses Lenz's law, which says the EMF is equal and opposite the rate of change in magnetic flux. Therefore, the current is the negative rate of change of flux divided by the resistance of the ring. Next, I wrote code that would find the magnetic force on the ring. This stems from the formula for the magnetic force IDL cross B. After calculating the magnetic force on the ring, due to Newton's third law, we know that the force on the magnet would have to be equal and opposite the force on the ring. Next, I found the net force, which is the magnetic force on the magnet plus the gravitational force on the magnet, mass times the gravitational constant. And finally, I used Newton's second law to calculate what the final velocity and position would be. We can use Newton's second law to find the acceleration of the magnet, and using kinematics, we can find the new velocity and the new position. Here's what the simulation looks like when run. Which color corresponds to the clockwise current and which to the counterclockwise current? For a red loop below the magnet as it falls, the magnetic field points up and gets larger and larger, meaning the change in flux would point upward, and according to Lenz's law, the magnetic field from the induced current would be in the opposite direction of the change in flux, so downward. Due to the right-hand rule, the current would have to flow in the clockwise direction to produce a B field in that downwards direction. Therefore, the red represents a clockwise direction and the blue represents a counterclockwise direction. The diagram on the left shows how I determine this. Now what happens when the dipole magnet is flipped? The magnet will still fall at the same speed. The difference will be that the current above the magnet will be in the clockwise direction and the induced current below will be in the counterclockwise direction. The diagram on the right shows how I determine this. The flipped dipole magnet results in a reverse B field from the magnet, so the induced currents in the tube will flow in opposite directions from before, and an upward force will still be exerted on the magnet. How do the results compare? The time for my computational model is significantly larger than my experimental time. After testing different dipole moments, I believe this is due to the fact that the dipole moment I found in Lab 3 was too large. The larger the dipole moment, the stronger the magnet, meaning it would induce a greater current and therefore move through the tube much slower than a magnet with a smaller dipole moment. Still, the computational model should provide a more accurate representation of the situation because in the real world there is air resistance that would provide a force on the magnet as well as the small force that my hand may have given the magnet as I dropped it through the tube. These added forces could affect the results of the experiment. And finally, what does the graph tell us? As the magnet is in the tube, it reaches a constant velocity, meaning there is no acceleration and there must be a net force of 0. This would mean that the force from the tube would be equal and opposite the gravitational force. If the resistance of the conductor was reduced as close as possible to zero, the induced current in the tube would be extremely large and would therefore exert a greater force on the magnet, making it fall even slower. If holes or slots were cut into the tube, there would be much less induced current and therefore much less force exerted on the magnet, so it would fall faster through the tube. This concludes my presentation. Thank you.